Hello. Today we're going to go over similarity transformations. We've studied translations. That's one type of transformation. That's when the object is just moved. And then we have the rotational transformation and reflections. And of course, with a reflection and the rotation, we have to specify what it is we're rotating about. We've mostly rotated about the origin in this course, and our reflections were usually about the x-axis or the y-axis. But in all previous cases, we maintained the same size and shape. In other words, our transformed objects were congruent to the original objects. That's why they were called congruent transformations. Well, now we've got similarity transformations. These do not maintain congruence, but they do maintain similarity. In other words, the size does change, but just like with similar, say, triangles, each side is in the same ratio. For instance, this side, assuming this side corresponds to this side, the ratio of this side to this side is exactly the same as the ratio of this side to this side. Now when we're performing a dilation, which is another name for a similarity transformation, it's called a dilation. Normally you would think of dilation as an enlargement. For instance, if your pupils are dilated, it probably means you're in trouble, but it also means that they're larger than usual. Well, in our case, dilation means larger or smaller. It could be a reduction, it could be an expansion. How do we note that in terms of K? K is our similarity factor. Just like before when we had similarity triangles, when we had similar triangles, we had a scale factor. We've got the same thing in the similarity transformation. We have a scale factor here. Well, is our transformation making let's say A is the original object, did our transformation to B make it larger or smaller? Well, we have to divide this up somehow. Say if K was negative, it makes it smaller, and K is positive, it makes it bigger. But that doesn't work. The way it does work is if K is less than 1, then our dilation is a reduction. If K is greater than 1, our dilation is an expansion. For instance, here, as we transform ABC to XYZ, K would be greater than 1. On the other hand, if we went the other direction and transformed XYZ into ABC, the K for that transformation would be less than 1. What about these little rays shooting out from the origin here? Well, if we produce a dilation with respect to the origin, let's suppose this is our original here, we can draw a ray from the origin through the point, in this case a triangle, but it would work with other polygons, to the corresponding point in the image. Just like with our other transformations, with a similarity transformation, we have the original polygon, or in this case triangle, and the image under the transformation. This is the image, and X, Y, and Z are the image points of A, B, and C. And the cool thing is, if we draw a ray through the origin and one point on the original figure, it will have to pass through the corresponding point on the transformed figure. And this is only true for similarity transformations. If we made some other type of transformation that totally skewed things, then this wouldn't be true. Everything I'm saying here applies only to similarity transformations. this is where we've got an origin here. We're expanding out this way. Suppose we kind of flip this around. So we've got our large one here, the small one's up here, and the origin is off there somewhere where we can't even see it. Does that remind you of anything? Well, if you never took an art class, it probably wouldn't remind you of anything. But this is very much like the perspective lines. When you draw a foreground and then you want the background to vanish properly, you draw these rays which all meet at a vanishing point, which would be somewhere off the page here. And if you put the corresponding parts of the original image right on the rays, you will get a triangle similar to this one. In other words, you will be performing a similarity transformation. Or to put it, maybe a more intelligent way to say it would be to place your transformation here, and you can always find rays which pass through and will converge at a vanishing point. This whole thing here is really just another way of looking at this. This doesn't look so much like a vanishing point unless you flip it around and look. This way, it's going off into the distance the way vanishing points in drawings normally do. So our similarity transformations are related to drawing and vanishing points. So if you're into art and hate math, well, you probably don't really hate math as much as you think you do, because if you're into art, then you're using math. And why the heck are we studying similarity transformation now and not back when we were studying all the other transformations? Well, we studied congruence transformations when we were studying congruence. Since we've spent this whole chapter studying similar polygons, it makes sense to study similarity transformations, because everything we're doing with these similarity transformations comes straight from everything we did with similar polygons. In other words, everything we know about similarity transformations, everything we're going to use, most everything we're going to use about similarity transformations comes directly from the previous sections where we studied similar polygons. This is really just kind of an extension of everything we've done the last 6 sections where we've studied similar polygons. So this section's actually, even though it seems like a new concept, it's not at all. It's just another way of arriving at things we're already familiar with, which is similar polygons. This will make a lot of sense when we start working some problems, so why don't we do that? I think that a lot of these concepts make a lot more sense when you actually use them to work a problem rather than just talk about them. Okay, now what we have here is a dilation using the origin. So we're going to use our scale factor. Remember, that's xy equals kx and ky. And remember, x and y have to be multiplied by the same factor. If it's different, then we're not going to have a polygon similar to the original one. If we say expand x by one factor and then expand or contract y by some other factor, well, I think it's obvious that we're not going to end up with anything like the original figure. For instance, I did that down here just to show you what would happen and why k has to be the same for both x and y. To go from here to here, I multiplied x by 4/3 and y by 2. Now I not only have a figure which looks bigger than this one, but it is not similar at all. Notice this one is much longer than it is high. This one is almost square now. I expanded x by 1 1/3, just a little bit. but I doubled y. And now this figure is, well, they're still both rectangles, but that's all you can say. They now have nothing in common. So this is not a similarity transformation. This is not a dilation. K, in other words, your multiplier here, has to be the same for both x and y. So back to this problem. What do we have for a multiplier? Well, let's see here. K is at the point 4, 0. Q, the corresponding point here. If we got P, Q, J, K. So assuming they wrote it correctly, the second letter corresponds to the second letter. This is the second letter in the original. This is the second one in the image. And we're supposed to write them in the same order so we can keep track of what corresponds to what. In this case, K corresponds to Q, and Q is just double K, isn't it? This is 4, and this is 8, I think. 1, 2, 3, yeah, this is 8. So we just found our scale factor. That has to be the same for everything. So if we find the scale factor for one point, we've found it for all of them. So our K now is, or to put it another way, we write that our transformation is now, oops, a little arrow. Gee, that is awful. So our notation should look like xy goes to 2x and 2y. So we've got this. We've got, in other words, we use this to get our scale factor, and I think L corresponds to R, yes. J corresponds to P, yes. This is the one we don't know. And it's good that we have the scale factor, because we could use proportions to figure out the length of these two missing sides, but we still have to have the angle at which they meet, and we don't have any way to figure out what this angle is, or any way to make sure that we've reproduced it when we get our two sides here. But luckily, we have this, and this tells us everything we need. All we have to do is take m, figure out what it is, and I would say that's -1, -2. And when I computed this, this is actually -4 and this is -8. So the scale factor is 2. I think maybe I said this is 4 and this is 8. Obviously, that's completely wrong. If this is -5, and this is -4, and this is -8. But luckily, it doesn't matter which side of the axis we put our objects on. The scale factor works out the same. So here we have -1, -2 is m. So just write m. Gee whiz, there we go. -1, -2. That would go to what? Well, -2, -4. Where the heck is that? Well, there's -2. And there's -4. So there's the point, -2, -4. And I just drew the lines in. It wasn't really required. But get an idea if it actually makes sense. And they certainly look similar to me. So -2, -4. Is that one of the answers, I hope? Yeah, here we are. -2, -4. And notice they did the usual stuff. Every single one of these has a 2 and a 4 in it. You could easily glance at this one and accidentally reverse the 2. Or you could ignore a minus sign like I did and get 2, 4. So be sure to pay careful attention when you're doing these on the standardized tests. They're going to throw answers at you that look just like the right answer. They're going to try to fool you. Here's one where some guy at the post office tried to do some geometry, and of course he got it wrong. What was the mistake? Well, it looks like he just took the length of this and the length of this and decided that the ratio of those two lengths was the dilation factor. Well, dilation factor, remember, you have to be able to use it like this. xy goes to kx and ky. K is not necessarily what you did to the length of any particular part of the polygon. In this case, it's only a line. It's true that this line here is 2/5 of this line, but that's not the dilation factor. To get the dilation factor, you need the coordinate for A and then the coordinate for C. And what is that? Well, this is 1, 1. So we have A is 1, 1. And that goes to 2.5 and 2.5. So this is going to 2.5, comma 2.5. Ooh, that's not that point. 2.5. Well, if 1 goes to 2.5, I'd say that's a dilation factor of 2.5. So AB to CD, the dilation factor is actually 2.5. It certainly is true that the length of AB over the length of CD is 2/5, but that's not the same as the dilation factor, not when you're dealing with coordinates. And that's kind of an important thing to remember, because this is an easy mistake to make. When you first look at it, it's pretty easy to say that if this is 10, this is 4, 4/10 is 2/5, boom, we're done. No. You have to use the coordinate notation when you're using a dilation factor. Well, looks like the post office is doing geometry again, making some small mistakes again. What did they do wrong this time? Well, first thing we should do is find the dilation factor. Remember, that dilation factor has to be the same for every single point. And it looks like, let's call this the original and this the image. Well, this point corresponds to this, and it looks like our dilation factor is 2. 2 times 4 is 8, 2 times 3 is 6. Looks good. What about here? Well, here, this is the point 8, 3, and this corresponds to the point 14, 6. Well, let's see. 2 times 3 is 6. 2 times 8 is 16. Uh-oh. Well, that's no good. That's the mistake. If you just glance at it, it kind of looks like a dilation, but you have to analyze it. And this point to this point, we may still have the same dilation factor as this, but this point here is no good. It needs to be out here a couple of more points, and we'd have it. If this line went like this, and that one like that, then we'd have a similarity transformation. But it didn't, so we don't. That's all you have to do, is just check and make sure that these dilation factors are the same for each point. And in fact, there's 2 reasons you couldn't use this. Not only does this double and this not, that messes it up right there, because k has to be the same for both x and y. So the fact that it doesn't match up these, that's part of the reason that it's not a proper similarity transformation, and the fact that over here we're not multiplying this by the same number. For instance, suppose this were 12 and 4.5. That would mean that we multiplied it by 1.5. And we multiplied each one by 1.5. So we got a number over here that made sense, but it still wasn't the same dilation factor as what's over here, which was 2. So it still wouldn't work. So there's at least 2 different ways we can say that this is no good. One, because k isn't the same for x and y, and one, because k isn't the same as it is over here. Yeah, this one's pretty easy. If we have a similarity transformation, do we? Well, it looks like we do. Let's check. Remember, if the original object has a point at the origin, that point won't move. So this is definitely a proper image. What about these two? Well, let's see here. This is, well, let's see here. If this is the point 6, 0, let's put it down here. E is 6, 0. Well, then, and B is 8, 0. So it looks like our dilation factor is 8/6 for this one. That's what it is for x. 8 over 6 times this will give us 8, so that's good. And of course that is 4 over 3. What about this one? Well, this is 4 and this is 3, so that is 4 over 3. So we have the same dilation factor each way. Well, it looks like we have, and of course here, that's right where it's supposed to be. The image under a dilation transformation, when dilated about the origin, is still going to be at the origin because, well, algebraically, k times 0 is still just 0. So we can put 4/3 times 3 is 4, and 4/3 times 6 is 8, and 4/3 times 0 is 0. So we have we know that they're similar. Now, the lengths of these, well, that's easy to compute because that's how we got our similarity transformation, is 4 to 3. So every single part of this image will be 4/3 of this. And 4/3 is the same as 1.33 or 133%. So that's C. Now this one's not bad. The short response is, if you dilate a figure using a scale factor of 2, and then dilate that image using a scale factor of 1/2, what's the size and shape of the new image? Well, the new image, after these two similarity transformations, is just the original image. Well, that's a short answer, isn't it? But why? Why would that be? Let's not even work it out with 2 and 1/2. Let's try k and 1 over k. So we first apply our transformation, which we know can be represented as k times x and k times y. Now we apply our next transformation. This transformation is our k transformation. What about 1 over k? If we apply it to this, what do we get? Well, we get 1 over k times k, x, and then 1 over k. Whoops. Times k times y. And of course all these k's cancel, and we're just going to end up with the same xy that we started with. If you perform your dilation using a scale factor of k, and then perform dilation on that image using a transformation of 1 over k, or a scale factor of 1 over k, we just end up right back where we started. Kind of makes sense when you think of it in terms of k times 1 over k. Just puts you right back where you started, doesn't it? And by the way, when you have something like that, in the future you may hear the word inverse transformation. That's exactly what they're talking about. The transformation which takes you right back to where you started. If your scale factor k, if you want to call that a k transformation or a k dilation, then 1 over k is your inverse transformation. I'm not sure if we'll use that term in this book, but it's a good one to know because it'll come up in many other math classes. Well, this one's pretty simple, I think. If these are dilations, and it says right here they are, so okay. All we have to do is figure out how they got to these dilations. And as long as we know one scale factor, if we have a dilation, then the scale factor has to be the same for x and y. Well, the scale factor here for x, it goes from 2 to 4. So I'd say it was 2. And for y, just to double check, it goes from 1 to 2. So we do have, for our first transformation, xy goes to 2x, 2y, or k equals 2. And for the rest of these, I will only list the transformation according to what its k value is, because that tells you everything you need to know about a dilation. Well, what's the next one? Let's say we're always going to just transform this one. In other words, we're not going to transform this first one into this, and then transform this into this, and then this into this. No, we're going to transform this into this, and transform this into this, and like that. Because of the even spacing here, you can play around with it, but I think it's pretty hard to find one number which you can multiply by this, and then multiply it by this to get this, and then multiply it by this to get this, and it's the same number every time. Because you had to multiply by 2 to get from here to here, but if you multiply by 2 to get from here to here, well, it's not going to work. Because this is going to be 4, and that's going to take you out to 8. So you'll get this one, but you'll miss the one in the middle. So going from this first one, why don't I just put a big A in the middle there and say that this is our original, and all the others are going to be images. Well, our first image is k equal to 2. We figured that out. Our next one goes from 2 to 6. Okay, how about k equals 3? And our next one goes from 2 to 6, 7, 8. Well, that's k equals 4. And we can just keep doing this. We could produce a whole, actually we could produce an infinite number of these. We could, as long as we've got numbers, we could write k equals 5, k equals 6, k equals 7. We can keep doing that until we run out of numbers. I don't know about you, but I've got lots of numbers. I bet you do too. By the way, that expression comes from a scene in a movie where a man doesn't understand how auctions work. So every time somebody bids, he just says a number higher. And at one point he says, I don't know why you think you can win. I've got lots of numbers. I can always say a number higher than yours. That's not quite how auctions work. Well, this one wants us to consider what happens if we allow our dilation factors to be negative. Remember, our notation is, for a dilation, is that xy goes to kx and k times y. So, this doesn't really look too bad in terms of figuring out what happens. If k is negative, well, all this is going to do, if we have a coordinate system here, I think maybe the easiest way to think about what happens when k is negative is to just think of a k with negative 1 multiplied. In other words, minus 1 times k becomes, so it's minus 1 times kx, and then minus 1 times ky. And Earlier, we showed a notation that we hardly ever use, but when we have a list of numbers separated by commas, for instance, xy, we can pull a number out, just like we would with the distributive property. Remember, if we had over here, let's write x plus y. Well, if this were ax plus by, we could write that as b times x plus y. The b distributes across these two. Well, it's funny, we can do the same thing if we have an ordered sequence of numbers here, just separated by a comma. We could put a minus 1 out in front, and that's meant to imply that's minus 1x and minus 1 times y. It just comes inside and multiplies right across. Why would I bother to tell you about this? Well, let's consider this here, and this one, minus 1k. If our dilation factor is negative, we could just call it negative k or minus 1 times k. So if we pull that out, then we've got kx and ky minus 1 times a minus 1, which is the same as saying a negative kx comma ky. Well, all that means is we simply reverse the sign of what's inside here. So if k is between 0 and 1, meaning that our transformation is a reduction, well, all this negative sign does is move it. If it was in, for instance, if the point, let's just remember each point in the transformed polygon gets moved exactly the same. So let's just say this is some point in our polygon. What's going to happen when we transform it by kx? Well, let's not worry about kx. Let's suppose this is already transformed. This is in the image. xy goes to kx and ky. Well, this is the image. This is kx and ky. It turns out to be the point 1, 1. Well, if it had originally been negative kx and negative ky, that's just minus 1 times the kx and the ky. If this is 1, 1, then it becomes minus 1, minus 1. Just like that. Suppose it was this point here, which is minus 2, 2. Well, then it becomes 2 minus 2. Notice what's happening? We just switch over to the opposite quadrant. If it was down here where both of them were negative, it'd come up here where both were positive. If it's down here where x is positive and y is negative, then it'll shift over here where x is negative and y is positive. There's very little difference in having a negative dilation factor. It really just changes the location. Doesn't change the size. As you can see over here, you put a negative sign in front of it. That doesn't change the length of anything. And in fact, we know that a dilation factor of 1, like in this case here, is a congruence. So if we had a triangle over here, and we just use a dilation factor of minus 1, all that's going to do is put the triangle right over here. But it will be a congruent triangle. It will be exactly the same triangle. It won't be similar, it'll be congruent. So the dilation, if k is between 0 and minus 1, well, let's pretend that k is between 0 and 1, and we just pulled the negative 1 out. Well, what does that mean? That means it's a reduction. That leads to a reduction. And The same thing happens if you're using the negative k, because like I said, just picture it as kx and ky with a negative sign out in front, which means that if k without the negative sign would reduce it, then it still gets reduced. If k without the negative sign would enlarge it, then it still gets enlarged. Same thing here. If k is less than minus 1. Well, if we pull out in other words, well, if we draw this to the left of negative 1 here, which means it's the same, once again, as if k was greater than 1, and then we just use the negative. If k is greater than 1, that's an enlargement. So when k is to the left of minus 1, that's also an enlargement, because remember, as you go to the left in the negative numbers, they get bigger. If you go to the right with positive numbers, they get bigger. So what this is saying is that the numbers are getting bigger starting at negative 1. In fact, negative 1 isn't even included. So every dilation with a factor of k less than minus 1 has to be an enlargement. And as far as a rotation, well, I think we already showed that. If this is at this point, 1, 1 switches over to minus 1. Well, how much of a rotation is that? That's just the full 180 degrees, isn't it? It's like a straight line. Same thing here. We get minus 2, 2 goes to 2 minus 2. Again, 180 degree rotation. There's more you could say about this. It'll always rotate here, but it also looks like a reflection about this line. So this point gets reflected about this line, or these 2 points got reflected about this other line. This line is the line x equals y, and this one is the line y equals x, I guess would be a smarter way to say it, and this line is y equals minus x. But for a rotation, you don't have to qualify it. It's a 180 degree rotation either way. And that's what happens when you make these negative. And you can fool around and try it. It's really, well, I just did down here. I mean, when you reverse the signs of what's inside, you're simply flipping quadrants. And that's the same as a 180 degree rotation. Well, that's about it for similarity. We'll have a review video. We'll go over standardized test problems taken from Similarity. And then, in this series, next is trigonometry. If your book might follow Similarity with quadrilaterals. In my series, quadrilaterals follows trigonometry, but they're independent. So, if your book shows quadrilaterals after the chapter on similarity, just skip trigonometry videos and go straight to the ones in quadrilaterals. After quadrilaterals, the next chapter in your book will be trigonometry. I can say that with a fair amount of confidence because every book I've seen follows pretty much the same order, except some of them put trigonometry in front of quadrilaterals, some of them reverse that. And that's about the only difference in the order in which this material is presented. And trigonometry is great. It's one of the most useful things you'll study in high school. It gets used all over the place. You couldn't hardly do anything in the modern world without trigonometry. Well, that's about it.